welcome back to my Amateur Radio FCC General License course. It's a wonderful day in the amateur radio neighborhood and all the bands are hopping. It's a great day to learn more about your new hobby and emergency communication source. Do you remember sitting in math or algebra class thinking, I'll never need to use this stuff. Why should I learn this? I know I sure did. Well, today you may wish you'd been paid more attention in class. We're going to cover some of the things. As we progress in our journey through amateur radio, math can be an important tool. And with a little diligence, effort, you will soon be able to tame that mathematical beast and become its master. Are you ready to learn? Well, let's get started. This is the Amateur Radio General Class License course, lesson number 5. I'm your instructor, KE2GS, Gary Stevens. That's Kilo Echo 2 Gulf Sierra. Subelement G5 covers electrical principles. There's 3 exam questions from the 3 groups of 43 questions. This covers the 2019 through 2023 General Class FCC Element 3 question pool effective July 1st, 2019. Subelement G5 covers electrical principles. We're going to be covering reactance, inductance, capacitance, impedance matching, the decibel, current and voltage dividers, electrical power calculations, sine wave root mean square values, peak envelope power calculations, resistors, capacitors, and inductors in series and parallel, and transformers, and how to calculate it all. Let's start out by reviewing some electronics terms. Resistance is basically friction against the flow of electrons. A resistor limits the flow of current in both AC and DC circuits. Reactance is basically the inertia against the flow of the current. In AC circuits, capacitors, inductors can also be used to limit the flow of current. Impedance, this represents all forms of opposition to the flow of current. This includes both resistance and reactance. So inductive reactance. Inductance is noted by the letter L, and the reactance formula is X sub L equals 2 pi FL. And with capacitive reactance, capacitance we know as C, and the reactance formula is X sub C equals 1 over 2 pi FC. And before you freak out, you don't need to know the reactance formulas for the general exam. Next, we're going to be talking about reactance, inductance, capacitance, impedance, and impedance matching. I like this meme because it kind of shows it in an interesting way, or an interesting perspective. So resistance, if you think of the cake as current, resistance is being able to just say no, push it away, get it out of your mind. Whereas inductance is you're taking it in, you're consuming it. And capacitance, you're holding it, you're keeping it. So this is a great slide, or a great meme, great slide of a meme. And one of the classic cases of opposition is the tug of war, when you're tugging between two factions. So we just need to know for the exam that opposition to the flow of current is in an AC circuit is called impedance. So in this example, the other person is impeding the other one from getting the rope. For the exam, we also need to know that the opposition to the flow of alternating current caused by capacitance or inductance is called reactance. So here again, I'm showing you the formulas. You don't need to understand them. It's just there as something to visualize that, whew, I don't have to remember that, but I do need to remember capacitive reactance and inductive reactance and how it affects things. So we were taught earlier that reactance causes opposition. So for the exam, you need to know that reactance causes opposition to the flow of alternating current in an inductor. Likewise, we need to know that reactance causes opposition to the flow of alternating current in a capacitor. I'm sure before you were wondering what F stood for in the formulas that was given, and F stands for frequency. For the exam, you need to know that as the frequency of an applied AC increases, the reactance increases, and it's how an inductor reacts to AC. With a capacitor, however, something different happens. For the exam, you need to know that as the frequency of the applied alternating current increases, the reactance decreases, and that is how a capacitor reacts to AC. You know how the universe likes balance? Well, in electronics, balance is a good thing as well. For the exam, we need to know that when the impedance of an electrical load is equal to the output impedance of the power source, assuming that both impedances are resistive, the source can deliver the maximum power to the load. So when you're in balance, you can receive more from the universe. Yeah, kids today will never know the joy of putting together a stereo system. But one of the things that was always a deal with a stereo system, maybe if you put one in your car, it's all about matching the loads or matching your impedance. One way that you can do this is with a transformer or a matching transformer. So for the exam, you need to know that one reason to use an impedance matching transformer is to maximize the transfer of power. So let's test your memory. Maybe you recall from the technician class about ohms, and we measured resistance in ohms. And here is a photo of ohms and the symbol omega, which is used for ohms. But ohms is also used to measure reactance. So for the exam, you need to know that the unit used to measure reactance is an ohm. I don't know about you, but every time I start talking about pi, I get a little hungry. Here's some familiar items, the symbol pi, which we'll get to in a minute. There's a transformer, and there's a length of transmission line showed to do some matching and impedance. And then we have something that's called the pi network. So the pi networks, if you look at their configuration and then you look at the pi symbol, you can see why they're called pi networks. It's because they resemble the symbol for pi. For the exam, however, you need to know that a transformer, a pi network, and a length of transmission line, all of these are correct, are devices that can be used for impedance matching at radio frequencies. So an LC circuit is also sometimes called a resonant circuit, a tank circuit, or a tune circuit. It's an electric circuit that's consisting of an inductor represented by the letter L and a capacitor represented by the letter C connected together. For the exam, you need to know that one method of impedance matching between two AC circuits is to insert an LC network between the two circuits. So now we're going to talk about the decibel, current and voltage dividers, electrical power calculations, sine wave root mean square or RMS and, values, and the peak envelope power calculations. Exciting stuff. Decibel is a unit of measure that measures the intensity of sound or a power level. It's done by comparing a signal with a given level and using a logarithmic scale. As you can see by the chart, there's a significant difference between 3 dB, 10 dB, or 20 dB when it comes to the power gain, which we're concerned with in amateur radio. For the exam, you just need to know that approximately 3 dB is the dB change that represents a factor of 2 increase or decrease in power. Now, to calculate the total current in a parallel circuit, we use a little bit of math. In this example, we can see that there's a 9-volt battery and some various resistors of various sizes. And by using Ohm's law, we can calculate how many milliamps are drawn by each resistor. We can sum the total once we know those values and come up with the total current in that circuit. For the exam, we need to know that the way the total current relates to the individual currents in each branch is a purely resistive parallel circuit is that each equals the sum of the currents through each branch. Some of you might freak out when you see this question on the exam. It's how many watts of electrical power are used in a 400 volt DC is supplied to a 800 ohm load. You have to do some math to calculate this. We're giving volts DC and ohms, but we need to somehow magically make it into watts. So let's see how we can do that. So I like using these little circles. All you have to do is remember the pi and the EIR and where they go. And then when you want to calculate for something, all you have to do is put your finger over what you're trying to calculate for. In our question, we need to solve for wattage, and before we can do that, we need to resolve our current issue. So we calculate for current. Current is E divided by R. So 400 volts DC divided by 800 ohms equals 1/2 amp of current, or 0.5 amps. So now we can use it to calculate our power. P equals E times I, or 400 volts times 0.5 amps equals 200 watts. For the exam, you just need to know that 200 watts is the electrical power are used if the 400 volts DC is supplied to an 800 ohm load. In this question, we're asked to solve how many watts are being used with 2 amps on a 12 volt DC light bulb. So we do the math, and 12 volts times 0.2 amps equals 2.4 watts. So the answer on this question is 2.4 watts is how many watts of electrical power are used by a 12 volt DC light bulb that draws 0.2 amps. So in the next question, we're given the amperes and the ohms, and in order to solve for the how many watts are used from this equation, we have to determine what the voltage is. So to determine the voltage, we look at our handy little circle and we put our finger or thumb over the E, so we see that we need to multiply current times resistance. So we were given 7 milliamperes and 1250 ohms. So 0.007 amps times 1250 ohms equals 8.75 volts DC. So we can take 8.75 volts DC and multiply it by our 0.007 amps, and we end up with 0.06125 watts, which is 61 milliwatts. So for the exam, you need to know approximately 61 milliwatts is how many watts are dissipated when the current of 7 milliamperes flows through a 1250 ohm resistor. And you can either, there's two ways to approach this. You can either memorize the answer to the question or memorize the answer and the question, or you can work on this math and learn how to do it on the fly. So here we're looking at peak to peak versus peak voltage. So you can see here that the peak to peak is from the negative swing to the positive swing, that whole the gap there. Peak to peak is actually peak to peak. So whereas peak voltage is just a portion of that. You might encounter this question on your exam. What is the output peak envelope power from a transmitter if an oscilloscope measures 200 volts peak to peak across a 50 ohm dummy load connected to the transmitter output? So in order to solve for the peak envelope power, we have to first solve for peak envelope voltage, and that's a simple formula: peak to peak voltage divided by 2. Easy enough, right? The peak envelope power, we have to remember the formula is peak to peak divided by 2 times a factor of 0.707, like an airplane, 707. And we take the result of that, and we take to the power of second power, and we divide that by R. And you can see the math and the results there. Or you could just simply remember that 100 watts is the output peak envelope power from a transmitter if oscilloscope measures 200 volts peak to peak across a 50 ohm dummy load connected to the transmitter output. Take your choice. RMS stands for root mean square. It's defined as the square root of the mean square. It's also known as the quadratic mean. For the test purposes, you need to know that the RMS value is an AC signal that produces the same power dissipation in a resistor as a DC voltage of the same value. One test question you may encounter is, what is the peak-to-peak voltage of a sine wave that has an RMS voltage of 120 volts? Well, first, in order to resolve this, or to solve this equation, we have to first solve for the peak. So the peak is 120 volts times 1.414, and we get a peak voltage of 168.68 volts. Next, we have to solve for the peak-to-peak voltage, which is 168 times 68 volts peak times 2, which gives us 339.36 volts peak to peak. So if you want to do the math, that's great, or you could just remember this, that 339.4 volts is the peak-to-peak voltage of the sine wave with the RMS voltage of 120 volts. Another question you might be asked on the exam is, what is the RMS voltage of a sine wave with a value of 17 volts peak? Well, so with a peak of 17 volts, the RMS, or root mean square, is 0.707 times the peak. So that gives it an RMS value of 12 volts. Or you can just remember that 12 volts is the RMS voltage of a sine wave with a voltage of 17 volts peak to peak. This table shows some of the power loss percentages, um, decibel and then a percentage of loss. For the exam, you need to know that 20.6% is the percentage of power loss that would result from a transmission line loss of 1 decibel or 1 dB. What would an exam be without a trick question? So the question on the exam would be, what is the ratio of peak envelope power to the average power for an unmodulated carrier? Okay, so the trick is, because there's no modulation, the average and the peak envelope power are the same, thus the ratio is 1. So for the exam, know that 1 is the ratio of the peak envelope power to the average power for an unmodulated carrier. I hope you're not like me and slept through the square roots portion of math class. You'll find on the exam a question that says, what would be the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? Okay, to resolve that, we need to find the voltage RMS. So to do that, we have to take the square root of power times resistance. So in this, we're given the power of 1200 watts and a resistance of 50 ohms. So that results in 60,000, and we need the square root of that, which gives us 244.9489743. And by the way, you are allowed to use a calculator. So I would recommend for this exam, if you're going to do the math, take along a scientific calculator that does not store memory or does not have any memory. So you can't use a TI fancy calculator that you can store formulas and things in. That's not allowed. But just a cheap calculator is allowed. And if you don't want to do the math, just remember that 245 volts would be the RMS voltage across a 50 ohm dummy load dissipating 1200 watts. And we have another trick question. The question, if you find one that says, what is the output peak envelope power of an unmodulated carrier if an average reading wattmeter connected to the transmitter output indicates 1060 watts. Okay, again, because there's no modulation, the average peak to peak, or average and the peak envelope power are the same. So just remember this, that 1060 watts is the output peak envelope power of an unmodulated carrier if the average reading wattmeter connected to the transmitter output indicates 1060 watts. So they're equivalent, 1-to-1 ratio. Life is good. Another question on the exam. What is the output peak envelope power from a transmitter if an oscilloscope measures 500 volts peak to peak across a 50 ohm resistive load connected to the transmitter output? Okay, so first we have to remember the formula, which is PEP equals PEP times 0.707 squared divided by R. So we plug in the values. We know that we have 500 volts peak to peak, and we know that there's 50 ohms. So that gives us a formula of 500 divided by 2 times 0.707 squared divided by 50. So that gives us 250 times 707 squared divided by 50, which comes out to 176.75 squared divided by 50, which is 32,240.56 divided by 50, which gives us a result of 624.1 81125. So you round that off, and it's 625 watts. So you could just remember that 625 is the output peak envelope power from a transmitter if the oscilloscope measures 500 volts peak to peak across a 50 ohm resistive load connected to the transmitter output. So that puts the hard stuff behind us, or the tougher math. We get into a little bit easier. For some of you it may be a little difficult, but for some it will not be. So this next section, we're dealing with resistors, capacitors, and inductors in series and parallel, and we're also going to be talking about transformers. So mutual inductance is the basic operating principle of transformers, motors, and generators, or any electrical component that interacts with a magnetic field. We can define mutual inductance as current flowing in one coil that induces voltage in an adjacent coil, as you can see in this diagram. For the exam, you just need to know that mutual inductance causes a voltage to appear across the secondary winding of a transformer when an AC source is connected across its primary winding. So a test question would be, what happens if a signal is applied to the secondary winding of a 4-to-1 voltage step-down transformer instead of the primary winding? So basically 4-to-1, so you know you're dealing with the factor of 4. So the answer would be, or what you need to remember for the test, is the output voltage is multiplied by 4 when a signal is applied to the secondary winding of a 4-to-1 voltage step-down transformer instead of its primary winding. So to answer the next question, we need to understand that when you add resistance in series, it increases the resistance. When you add it in parallel, it reduces the resistance. So for this exam, the question reads, which of the following components increases the total resistance of a resistor? So for the exam, you just need to know a series resistor increases the total resistance of a resistor. On this question, we're asked, what is the total resistance of 3 100 ohm resistors in parallel? When they're all the same value, it's really easy to calculate. You just simply divide by the number of resistors. So in this case, they're all 100 ohms. So the formula would read resistance total, or R total, equals R divided by N, but it's only if they're equal value. So with our formula, R total equals R divided by N, where 100 divided by 3 is 33.333. For the exam, we need to know that 33.3 ohms is the total resistance of 3 100 ohm resistors in parallel. For this question, we're giving a total resistance, and we need to solve for the resistors of equal value. So the question reads, if 3 equal value resistors in series produces 450 ohms, what is the value of each resistor? So we know that R total equals R1 plus R2 plus R3. So from that we could derive a formula, R equals R total divided by N, or the number of resistors. So our value is 450, and we have 3 resistors, so the answer is 150. For the exam, you just need to know that 150 is the value of each resistor if 3 equal value resistors in series produce 450 ohms. If you get this question, what is the RMS voltage across a 500 turn secondary winding of a transformer if the 2250 turn primary is connected to 120 volts? Well, the output voltage of 120 volts times 500 divided by 2250, which gives us the ratio. When we do the math, it comes out to 26.7 volts, rounded off. So you could either do the math, or you can just remember that 26.7 volts is the RMS voltage across a 500 turn secondary winding of a transformer if the 2250 turn primary is connected to 120 volts AC. Oh my gosh, I led you guys astray. So the next question does deal with square roots. So the question reads, what is the turns ratio of a transformer used to match an audio amplifier having 600 ohms output impedance to a speaker having 4 ohms impedance? That's quite a jump. So the turns ratio equals to the square root of the impedance ratio. So the formula is turns ratio is the square root of 600 divided by 4. So 600 divided by 4, which is the ratio, gives us 150. So the square root of that is 12.24744,871, which we round that off to a turns ratio of 12.2 to 1. So you could do the math, or you can just remember that 12.2 to 1 is the turns ratio of a transformer used to match the audio amplifier having 600 ohms output impedance to a speaker having 4 ohms impedance. That's maybe a little easier for some of you to just remember that. For this next part, we need to do a little metric review, or metric system review. We should remember from our technician class, or maybe science class in high school or college, that milli means 10 to the negative third, micro is 10 to the negative sixth, nano is 10 to the negative ninth, and pico is 10 to the negative 12th. You may have this question on your exam. What is the equivalent capacitance of two 5 nanofarad capacitors and one 750 picofarad capacitor connected in parallel? So we remember that 1 nanofarad equals 1,000 picofarads, and we also know that when we put capacitors in parallel, we add them. So that gives us the equation 5 nanofarads plus 5 nanofarads plus 0.750 nanofarads, because we converted the pico to nano, equals 10.75 nanofarads. So for the exam, you need to know that 10.750 nanofarads is the equivalent capacitance of two 5.0 nanofarad capacitors and one 750 picofarad capacitor connected in parallel. Another question you might have on the exam is, what is the capacitance of three 100 microfarad capacitors connected in series? Well, we should remember that capacitors in series are calculated like resistors that are in parallel. So this C total, or capacitance total, equals 100 microfarads divided by 3, which gives us a capacitive total of 33.3 microfarads. So for the exam, you could just remember that 33.3 microfarads is the capacitance of three 100 microfarad capacitors connected in series. Another exam question we might have is, what is the inductance of three 10 millihenry inductors connected in parallel? Okay, so inductors in parallel are calculated like resistors that are in parallel. So the inductance total, because they're equal, is 10 millihenries divided by 3, which gives us a total inductance of 3.333333 millihenries, which averages out to 3.3. For the exam, you could just simply know that 3.3 millihenries is the inductance of three 10 millihenry inductors connected in parallel. Another possible question is, what is the inductance of 20 millihenry inductor connected in series with a 50 millihenry inductor? Okay, with inductors, they're just like resistors in series. We add them. So the inductance total would be simply 20 millihenries plus 50 millihenries, and simple math would tell us that that's 70 millihenries. So for the exam, know that 70 millihenries is the inductance of a 20 millihenry inductor connected with a series with a 50 millihenry inductor. Some of you may look at this question and say, what in the world have I gotten myself into? Well, it's not as bad as it seems. So the question might read, what is the capacitance of a 20 microfarad capacitor connected in series with a 50 microfarad capacitor? Well, the total value for series capacitors is the reciprocal of divided by the reciprocal of C1 plus the reciprocal of C2. So when we plug in the values and do the math, we end up with 14.285 microfarads. But then for the exam, you could just simply remember that 14.3 microfarads is the capacitance of a 20 microfarad capacitor connected in series with a 50 microfarad capacitor. So capacitors, we just need to remember that when you put capacitors in parallel, it's equivalent to one bigger one. So you just take the sum. So a capacitor in parallel should be added to a capacitor to increase its capacitance. And that's a test question. And likewise, you could tell from the math earlier that series inductors or inductors in series add, just like they would with a resistor. So for the exam, you just need to remember that an inductor in series should be added to the inductor to increase the inductance. I remember when I was in the Navy and we reached this portion of our training for electronics, and we didn't have calculators. We had to do all this by hand, and it was just, it made me cringe. But with calculators, it's not as bad. So you might get the question, what is the total resistance of a 10 ohm, a 20 ohm, and a 50 ohm resistor in parallel? So again, we're talking about the reciprocals. So you can see that the 1 over R total equals 1 over 10 plus 1 over 20 plus 1 over 50. So if we do the math, that all comes to 5.882352941, which rounds to 5.9 ohms. So you could do the math, remember the formulas, or you could just simply remember that 5.9 ohms is the total resistance of a 10 ohm, 20 ohm, and 50 ohm resistor connected in parallel. In this photo, you can see a transformer, and you can see the larger wires, which are connected to the primary winding as compared to the smaller wires connecting to the output. For the exam, you need to know that the conductor of a primary winding of many voltage step-up transformers are larger in diameter than the conductor of the secondary windings in order to accommodate a higher current of the primary. So if you use the Ohm's law, what you get in is what you get out as far as current. So you need a higher current on one end to get the higher voltage on the other end. In electronics, it's important to be able to translate between micro to nano, or nano to pico, or pico to nano, or pico to micro, or even to milli. For the exam, you need to know that in order to go from 22 picofarads into microfarads, you would simply divide by 1,000. You can see the pico is 10 to the minus 12th, nano is 10 to the minus 9th. That's 3 zeros in between. So to go, you just simply divide. Or you could just understand that 22 is the value in nanofarads of a 22,000 picofarad capacitor. In this slide, or the next question, we're asked to go from nanofarads to microfarads. So again, the nano is -9 and the micro is -6. There's 3 zeros in between, so we know that we're dealing with 1,000. So given the 4,700 nanofarad capacitor, we simply divide it by 1,000 and come up with 4.7 microfarads. It's simple math, but if you don't want to do the math, just remember that 4.7 is the value in microfarads of a 4,700 nanofarad capacitor. Congratulations, you made it through lesson 5. Does your brain hurt? I know at one point in my life that made my brain hurt, but it does come easier if you practice, and having a calculator makes life a lot easier. Well, I hope you've enjoyed today's lesson and have the tools you need to soldier on. Can you believe that we are at the halfway point already? Just 5 more sections to cover, and it will be history. You'll be ready for the exam. If you have not done so, please subscribe by clicking the links below. Feel free to post any comments or questions, or even hit the like button. Until next time, be safe, be well, and never stop learning.